Everyone, welcome to Dr. Ravi's Academy. I am Dr. Ravi, Professor of Mechanical Engineering. In today's lecture, you will be learning the analysis of compound stresses, an important topic of mechanics of solids, which is also known as strength of materials. In this particular class, you will be learning how to derive an expression for the normal and shear stresses when it is subjected to biaxial stresses with shear. Now, I am going to draw the schematic diagram of an element. Let us consider an element which is subjected to sigma x and sigma y along x and y axis, and it is subjected to shear stress tau xy also, tau xy. Let us assume that this element is A, B, C, D. This is a more practical approach, as you know, in fundamentals of strength of materials, that is in first unit of your syllabus, simple stresses, which is an idealistic approach. And if you look at this, usually you will come across with the body subjected to biaxial stresses, or that is compound stresses, you can say it is compound stresses, and your intention is you want to calculate in which direction the maximum stress is possible. With that intention, you are going to derive the expression for the normal as well as shear stress. For that purpose, let us consider a plane at an angle phi with the vertical line, that is CD, and this point I am calling it as E. Now, my interest is I would like to analyze this triangular element CDE and the stresses acting on that. I would like to consider the equilibrium of this triangular element by converting the stresses with the multiplying appropriate normal area and the bearing area, so that the element is in equilibrium. Let me draw the magnified view of this particular element. Here you have sigma x, sigma y, and tau xy horizontal and tau xy vertical. Apart from this, when you cut the element, let us assume that you have a normal stress sigma perpendicular to the plane DE, and along this surface ED, that's what is your shear stress tau. This is at an angle phi, and the element is CDE. Now, this is the element we are focusing on this, and let us convert the stresses by multiplying with appropriate areas. Let us assume that this element is having a unit thickness. The perpendicular to the blackboard, the thickness is unit thickness, and I am converting this into, with multiplying, CD is the length and the thickness is 1. So when you multiply with the CD sigma x, it becomes a force, and tau xy, the contact area, again CD. Similarly, sigma y, which is acting vertically upwards, this area is you multiply with the EC. The length is EC and the thickness is 1 unit. Similarly, the horizontal shear force, that is EC multiplied with 1 unit thickness, and where you have got this element, it is sigma into ED. ED is the length and the thickness is unit, and tau also, if you multiply with the ED, and it is converted into the forces. Now, my interest is I would like to represent all these forces on a coordinate axis. Observe carefully, along the horizontal axis you have sigma x, which is multiplied with the CD. This is one force, and the other force is tau xy, this force multiplied with the EC. These are the two forces. To the right it is acting one force and another force. Vertically upwards, let us see sigma y into EC and tau xy into CD. So here the vertical force is sigma y into EC and another force is tau xy into EC, tau xy into CD, this force vertical upwards. So sigma y into EC, tau xy into CD. So these two you have considered, and now the unknowns. Your interest is you want to calculate sigma, that is normal stress, and tau, that is shear stress. So with that intention, so when you rotate, you turn this plane by phi, your sigma also going to turn it by phi. So this is at an angle sigma into ED at an angle phi with the horizontal, and of course perpendicular to it you have tau into your ED. This is at an angle phi. So if you extend it, this is phi, and if you extend it, this is also phi. Now you have represented all the forces of this triangular element on a coordinate axis. Now I would like to write the expression for sigma as well as tau. So let me consider first a sigma, and I am writing it is sum of all the forces along the normal direction. I am writing sigma f along the normal direction is equals to 0. This is my equation of equilibrium along the normal direction. This is what is normal direction. This is normal direction, right? And of course this is the tangential direction. I am representing it by t. So let us look at these forces here. Sigma into ED, which is pointing in negative direction. Let me write it as minus. And let us look at that the component of these two forces along this, and the component of this along this, tau also, tau becomes 0, and you have 2 and 2. So 1, 2, 3 forces. These components let us write down. It is it becomes a plus, it is sigma x into CD. The component of this, it is cos phi, and tau xy, again it is a plus tau xy into EC cos phi. You have considered these two forces. The components are cos components. Now these two forces vertically upwards, component along this becomes sine component. You can write down it is again plus, because it's pointing toward the normal direction. That becomes it is a sigma y into EC. This becomes a sine phi, and the other force, that is plus tau xy into CD, there is also sine phi, is equals to 0. This is my equation of equilibrium along the normal direction. Let me keep this sigma left hand side, and let us take all the other terms to the right hand side. Let me write in detail. Now it is this becomes positive sigma into, it is ED is equals to, let me take the other side, all are positive. I have taken this to the left hand side. It is sigma x CD cos phi plus tau xy EC cos phi plus sigma y EC sin phi plus tau xy CD sin phi. Now let us look at this triangle CDE. From this triangle you can write down Sin phi is equals to opposite side EC by hypotenuse ED. Similarly, cos phi is equals to adjacent side CD divided by hypotenuse ED. So these values you can substitute into this. Now let us divide the right hand side with ED. Now you have expression for sigma. Sigma is equals to, it is sigma x CD by ED into cos phi plus tau xy EC by ED into cos phi plus sigma y EC divided by ED into sin phi, and the last term is plus tau xy, it is a CD by your ED into sin phi, into sin phi. Now let us replace CD by ED with cos phi, and you can write down sigma is equals to, already you have one cos phi, this becomes sigma x cos square phi plus your tau xy EC by, of course it is EC, this gets cancelled, you have cos phi plus EC by ED. EC by ED is sin phi, and that becomes sigma y into, it is sin square phi plus the last term tau xy, and it is CD by ED. Here this EC by ED, here EC by ED, EC by ED is sin phi. So you have here cos phi and sin phi, and the last term tau xy, here it is sin phi is there and this is cos phi. So you have sin phi and cos phi. Now let us simplify further. Write down here sigma x cos square phi plus sigma y sin square phi plus tau xy sin phi cos phi, tau xy sin phi cos phi. This becomes, it is tau xy 2 sin phi cos phi is sin 2 phi, sin 2 phi. And you can expand this, it is sigma x into cos square, you can write down it is cos 2 phi by 2 plus sigma y into 1 minus cos 2 phi by 2 plus tau xy sin 2 phi. And lastly, the expression you can write down sigma is equals to, it is sigma x plus sigma y by 2, and you can write down sigma x, here the other term is minus, this becomes minus sigma y by 2 into cos 2 phi, I have taken cos 2 phi as common factor, plus tau xy sin 2 phi. This what is the required expression for the normal stress. Thank you.